All right, and now here is our video on matrix multiplication. Note that we are going to rely on the previous video, the special case of matrix multiplication. So you need to watch that one first in order to understand what's happening in this one. So, in order to multiply two matrices together, the number of columns in the first matrix must be the same as the number of rows in the second matrix. It is written there correctly. So now let's look at our examples from the last video. And in the last video, when we were doing the special case, a row times a column, we said the number of elements had to be the same. This really is the more general form of that statement. The number of elements is 4 because there are 4 columns. Since it's a single row, the number of elements is the same as the number of columns. And the number of elements in a column matrix is the same as the number of rows. So here, the number of columns is the same as the number of rows. They're both 4 columns and 4 rows. In the example at the bottom of this page, I had 5 columns in my row matrix and 5 rows in my column matrix, and we were able to do that multiplication just fine. And then in the other example that we had, let's see, 6 columns in my row matrix and 4 rows in my column matrix. And remember, we said this is not defined. The problem was when we started to match up our elements in order to multiply, we ended up with extra elements over here that didn't have a partner over here. So, let's see, we will come back to this idea that the number of columns in the first matrix must be the same as the number of rows in the second matrix. Then, it's also important to know that the result will have the same number of rows as the first matrix and the same number of columns as the second matrix. So, we're going to look ahead to one of our examples. We're not going to figure it out just yet. But I'm going to write down my sizes. Remember, rows always come first when we're writing down the size. So this is 3 rows and 2 columns. So this is a 3 by 2 matrix. This is 2 rows and 3 columns, so this is a 2 by 3 matrix. So here, notice that, as we said here, in order to multiply, the number of columns in the first, which is 2, must be the same as the number of rows in the second, which is also 2. And it turns out that those numbers will always be the ones that are right up against each other if you write the sizes out this way. These 2 numbers must be the same. And then the result will have the same number of rows as the first matrix, that's 3, and the same number of columns as the second matrix, which is also 3 in this case, although these 2 numbers don't have to be the same. It's only the inside numbers that need to be the same. But I'm going to make a note that my result will be a 3 by 3. Okay, we'll come back to that in just a second to actually calculate that, but first we need to know how. So, remember our double subscript notation tells us, the first number tells us the row, the second number tells us the column. So C sub ij is row I, column j. Now, I do want to point out that this I is not the imaginary unit. This is not the square root of -1. That might be confusing when you first start working with matrices. It is traditional to use I as what's called an indexing variable, which is why we use I to stand for the word index. And that I is just a variable that tells me the row number. So to find element C sub ij in the result, you multiply row I from the first matrix by column j from the second matrix. So now, let's actually look at that example that we just set aside. And, well, we will figure this out. So we said the result will be a 3 by 3. So I multiply row 1 times in the first matrix times column 1 in the second matrix. Rows will always come from the first, columns will always come from the second. So row 1, so I have 3 times 1, which is 3, plus -2 times -10, which is positive 20. So in this position, I have positive 20. Well, I'll go ahead and write out 3 plus 20, which will be a positive 23. Now, for the second position, whoops, I'm in row 1, column 2. So I want to multiply row 1 times column 2. And maybe I'll draw some blanks here to help me with my organizing. It's a 3 by 3, so I know there's going to be 3 rows and 3 columns. So I have 3 times 0 plus -2 times 5. So 3 times 0 is 0. -2 times 5 is -10. And then finally, in the first row, I'm in row 1, column 3, so I want to multiply row 1 times column 3. So 3 times 3 is 9. -2 times positive 1 is -2. Now, some people like to simplify these right away. Either way is fine. But notice that my first row turns out to be 23, -10. 9 minus 2 is 7. So there's my first row. Now let's do our second row. Again, the row always comes from the first matrix. In order to find this spot, I'm going to multiply row 2 times column 1 because this spot is in row 2 and in column 1. So 2 times 1 is 2. 0 times -10 is 0. And for emphasis, I'm putting the plus 0. That, of course, can be omitted. 2 times 0 is 0. 0 times 5 is 0, so that's 0 plus 0. And finally, 2 times 3 is 6. 0 times 1 is 0. So when you have a 0 in a matrix or a coupled zeros in a matrix, it really does make the arithmetic nice. So my second row is 2, 0, 6. And finally, when I'm calculating row 3, I'm going to use row 3 from the first matrix. I'll have 7 times 1 is 7. And 4 times -10 is -40. 7 times 0 is 0. 4 times 5 is 20. 7 times 3 is 21. and 4 times 1 is 4. All right, and then finally I just need to reduce these to single numbers. 7 minus 40 would be negative 33. 0 plus 20 is 20. And 21 plus 4 is 25. And so there is my result matrix. Once you know how to multiply a row times a column, finding the entire matrix is not that bad. It's just multiplying lots of rows times lots of columns. So now let's do, oops, sorry, kicked my camera a little. Let's do this next one. Again, first, I have to see if the sizes match. So I've got a 2 by 3. And this one is a 3 by 2. Remember, when you're writing down the sizes, the rows always come first. That means I am able to do this multiplication because my numbers that are right next to each other here are the same. The number of columns from the first matrix is the same as the number of rows from the second matrix. My result this time is going to be a 2 by 2. So result will be a 2 by 2. So I'm going to lightly draw myself some blanks here. When you're doing this, you may just want to leave enough blank space. All right, so for row 1, column 1, I'm going to multiply row 1 times column 1. Now, it's not strictly necessary to circle your rows and your columns, but it can help people focus. So 1 times 3 is 3. 0 times 2 is 0. And 3 times 7 is 21. So I do have to add all those up. I might wait a moment, but notice that my answer for that spot will be 3 plus 0 plus 21. My answer for this spot will be row 1 from the first matrix times column 2 from the second matrix. And this is 1 times negative 2 is negative 2. 0 times 0 is 0. And 3 times 4 is 12. All right, let's go ahead and simplify that first row. So 3 plus 0 plus 21 will be 24. Negative 2 plus 0 plus 12 will be 10. And now when I'm doing row 2, this is row 2, column 1. So I'm going to multiply row 2 from the first matrix by column 1 from the second matrix. Negative 10 times 3 is negative 30. 5 times 2 is 10. And 1 times 7 is 7. Then finally, I've got row 2, column 2. So I'm going to multiply row 2 from the first matrix times column 2 from the second matrix. Negative 10 times negative 2 is positive 20. 5 times 0 is 0. And 1 times 4 is 4. So here I've got negative 30 plus 10 is negative 20. Plus 7 is going to be negative 13. And then 20 plus 0 is 20. Plus 4 is 24. Now, I do want to point something out about these two examples. Notice that I used the same two matrices in opposite order. Now, when we're doing multiplication with numbers or with variables that represent numbers or anything that we're used to doing multiplication with, we're always able to switch order. That's called the commutative property. You're able to change the order, you're able to move things around, and it doesn't change the product. But notice here, when I changed the order, I did change the product. Now, both of these I was able to calculate, but I got a different answer each time. And in fact, I got a different size of answer each time. And that can happen. That does happen with matrices. Matrix multiplication is not commutative. Order does matter. Okay? That is something that's very important to know about matrix multiplication. So let's do a couple more examples. All right. Here we have a 3 by 1. So I've got a 3 by 1 matrix for my first one, 3 rows and 1 column, and a 1 by 4 matrix for my other one. Notice this is not the special case that we were talking about earlier, where we had a row times a column. This is a column times a row, which, as it turns out, we will be able to calculate this. These numbers are the same, so this will work. My result will be a 3 by 4 matrix, which will be pretty large. So when I multiply row 1 times column 1, well, there's only one thing in each row and one thing in each column, so that means each element is going to be pretty easy to calculate. So 6 times 4 is 24, and that's my first position. So when I multiply, let me actually draw out my spots. So I have, it's a 3 by 4, which means 3 rows and 4 columns. So that's the correct number of spots. So when I multiply to get this spot, I need row 1, column 2, because this is position row 1, column 2. So 6 times negative 1 will be negative 6. 6 times 5 will be 30. 6 times 11 will be 66. Okay. Notice that it is the fact that, well, I have a column matrix times a row matrix that makes this sort of special in that each individual number is so easy to figure out. All right, well, let's just keep going with this. So 2 times 4 is 8. 2 times negative 1 is negative 2. 2 times 5 is 10. And 2 times 11 is 22. Notice here there's no pluses in between because each row in my first matrix and each column in my second matrix consist of a single element, which makes these easy to calculate. And then finally, 5 times 4 is 20. 5 times negative 1 is negative 5. 5 times 5 is 25. And 5 times 11 is 55. And there is my result. So now, notice I've decided to do the same, whoops, nudged it, same sort of thing we did last time. I'm switching the order. So we want to see if anything different happens here. I've got a 1 by 4 and a 3 by 1. These, however, are not the same. Which means if I were to try to multiply this row times this column, I don't have enough elements to properly match up. And that actually makes this one the simplest one of all to answer, because since the size does not work out, my answer is just not defined. And now you can work the practice problems, the rest of the practice problems, and check your answers on the matrix multiplication handout.